Hello, today I'm going to have a continuation of my previous lectures on potentials. Now, here I just want to give an in-depth treatment of what is the practical application of potentials, specifically in materials engineering. Brief and we want to have a brief recap of what we have discussed. Okay, specifically centers around this curve. Okay, now just a summary. So when you have an atom that approaches another atom, of course the electron cloud of the other atom is negative and the charge of the other atom is positive because of the proton in the center. Now they get attracted because that is a universal concept in physics that unlike charges will attract. Okay, so they will try to get as close as possible. That is the attractive energy. Okay, the blue curve. Now there will come a time that this attraction will be overpowered by the repulsive energy. Why? Because the electron cloud of the approaching atom is will get as close as possible to the electron cloud of the other atom, so they will try to have an interaction. It's quite repulsive, so that's the green curve. Now, of course, the total interaction is some of the attractive and the repulsive part. So we have a nice curve like this one, the red curve. Now, in the red curve, there is an E sub O. So that's the potential well. Okay, that's the minimum value. So normally, that is where the bonding will occur, whether it is valently bonded or physisorb in the system. So you will have an optimized value, a minimum, such that the energy associated with the potential is minimum. And of course, there is a corresponding bond length, or that's what you call interatomic separation, R. Okay, so for the minimum energy value of its interaction, there corresponds a optimized bond length. So that's fairly enough. That's the simplest way to explain it. Let's do more applications for it. Okay. So here, I want to generate a potential curve. Why do we want to do that? Well, I'll tell you. I'll tell you later. Okay. Now, in order to generate a potential energy surface, I have written a very simple program. Okay. So this is written in Perl. So the purpose of this is a molecule, we place it in a series of points that gets as close as possible to the nanomaterial. Okay. So we try to adjust the length such that it will approach the other side of the material. Okay. So we use a document. The document is called TI. Okay. So that's a very simple explanation. It's a very simple program that calls upon TI. Okay, what's a TI file? As you can see, the TI file is this whole thing. This is a nanomaterial, which is a very simple one because this is just a simple demonstration. So we have a nitrogen here that is represented by the blue balls, and we have the pink balls as boron. Now, for some reason, I want to add a metal, titanium. We have discussed that in the previous lectures that metals, they have a good affinity with respect to gases. Now, the gas that we are considering here is a very simple. It's a hydrogen. It's diatomic. So let's start. Okay. So that's the TI file. If you haven't been exposed to programming, this is a very simple demonstration. So you don't need to too complex stuffs here. It's a very simple explanation. I will try to lower it down so that the content about the potential is enhanced. Okay. Now we want to create a table. Okay. The output file is pes.std. So you have a file there, the output file. All of the files, all of the data will be outputted there. Okay, so it's a document. Now we want the small molecule, which is hydrogen, to be represented as X. Okay, as you can see, the hydrogen is represented by X. Okay. Okay. Now we have this output file again, which is the PES, and it's essentially an Excel sheet. Then in the Excel sheet there are columns. We have 3 columns. We have the structure, we have the distance, and we have the potential energy. So it's a simple output file which will contain the distance versus the potential energy. By the way, these column headings are just commands. Okay, we can look that up in the library. Okay, everything here that is in red is commands. Okay, so I select a calculator. The calculator will try to compute the potential. Okay, so the command for that is foresight. It's a simple calculator that I have uploaded in the program such that we can use that. Okay, so the command to call that is foresight. Okay. So here we try to start with the iteration. We iterate from 0 to 1.5 at an interval of 0.01 Armstrong. So the molecule X, which is the hydrogen, will come as close as possible to the nanomaterial in 0.01 increments. Okay. Again, we want to move the position of the hydrogen atom, which is X. So we have this command. Okay, we translate. Okay, and after the translation, okay, we call upon the foresight to calculate the energy. Specifically, that's the potential energy. Okay, so there is a syntax or a command for that, but essentially this is just a call for you to calculate the energy and the potential energy. Okay, so it will output the potential energy, the distance. Okay, and afterwards we get that file. Okay, and then we print that the program is complete, the script is completed. So let's try to start. Okay, so again, here's the initial configuration. Okay, so we now run the program. So I don't want to sit here and wait for the program to finish. We'll get back. Okay, when we get back, we will see what's the output. Okay, so hi, we're done. Okay, so we have generated the job is complete. So we have generated the file. Again, we have PES as the file name, and it displays distances and the calculated potential. Now I want to transfer that in, and here we have successfully transferred the distance and potential energy to Excel, and then we try to generate the potential graph. Okay, here we observe that as the hydrogen molecule will approach the nanomaterial, there is attraction, and then afterwards there is an abrupt change, which is repulsion. Why? Because the cloud of this hydrogen molecule will come in contact with the cloud of this nanomaterial. they are both negative because they are electrons in nature, so they try to repel each other. Okay, so if we have a zoom of this graph from 120 to 10, you can see the profile resembles the one that we have discussed in the book. Okay, if we zoom in further around 5, you see that here we have established the global minimum, or that is the potential well. That is where we have the absorption or the binding energy. That's the one that's the most preferable energy for the system, wherein there is an established bond distance between them that is 3 to 3.5 Armstrong. Okay, so we are here now in the fun part of our simulation. We try to apply this in a gas absorption system. Here, okay, I have designed a boron nitride tube. It looks like a tube because it has a circular cross section, and it's populated with boron, which is the pink, and nitrogen, which is the blue. If we try to elongate this along the z-axis, then we can see a more vivid tube. Okay. However, in this tube, I have randomly populated it with titanium metal. Okay. Why metal? Because metal has a good affinity towards gas. And we try to see what will happen if this is populated with gas. Okay. And I have done that here. Okay. Let's see. So as the simulation progresses, you will see that the hydrogen molecules are definitely attracted within the surface of the nanomaterial. You can see the density of the hydrogen is great around the surface of the nanomaterial, and it happens that the distance between the hydrogen and the surface is around 3 to 3.5, as we have discussed before. But there's a bonus. Take a look. These two nanomaterials, or this group of nanomaterials, are forming clusters. They are coagulating. They are forming these small islands as the simulation progresses. Why is that? So probably you know the answer already. I have generated a separate potential energy surface for the interaction of the boron nitride and the boron nitride. That's the reason why they get attracted to each other. Okay, so here we have already seen the application of potential energy surface. We can devise a gas absorption system, preferably that is hydrogen absorption system. Okay, that's all.